irregular area inside a square, and you are asked to calculate what is the total area of that irregular region. Okay, so how do you do calculation area? You take squares inside the irregular area. Suppose 1 millimeter, and count how many squares are there, and that will give you the area of that irregular region. Is that right? So you can be very smart also. You can just close your eyes, put a dot. Okay, see where it goes. Put a dot many times. You are just playing. Just put many dots. Then after a while you open your eyes and you look at that how many dots are in that irregular region and how many dots are in the total, the square. The square you know easily calculate the area. Suppose you find out of that 1000 spots, because you are very energetic, you are using your pen many times, 1000 times. Out of 1000, 900 went into the 100 only went into that irregular region. So you can think that, okay, out of this my area of that irregular space is 100 times the 1000. Out of 1000 only 100 went there, so it's only 10%. 10% of the area of the square. You can think. Then you compare with whatever you calculated with another way, see if it matches or not. That is what is Monte Carlo. Monte Carlo is you randomly choose some numbers, generate numbers randomly, and see that where it belongs to. Okay, if it belongs to that irregular area, then you know that okay, it goes there. If it is belonging to outside, then it is not contributing anything there. So Monte Carlo method is a statistical method with random numbers to calculate some things. Of course, when you are trying to do radiation transport, you are having a proton or electron beam or a particle going through the medium, so it is having different interactions. So you have to know how they interact. That kind of information has to be there. Okay, out of that, so doing a random generation of a number, you see that if that random number is matching with the probability of a certain interaction, then see that this is happening. If the random number is matching with the probability of other interaction process, then that is happening. So this way you decide what kind of interaction the particle is happening, particle is going through when it is passing through the medium. You are not solving an equation. You have already a probability density of different processes that can happen inside the when the particle is moving through the media. And then from this random number generation, you find which process is taking place, and if that interaction happens, what happens, how much energy is going to be deposited. So from there you can calculate how that energy is deposited in different regions. Okay, so this is what happens. You don't solve any equation. You have already some information about the system through which the particle is moving, and then you know the interaction, what are the interaction processes. In our case, we are doing Coulomb scattering. So you know that what is the probability of a Coulomb scattering, that depends upon the energy of the particle that is interacting, what are the electron density of that region, and from there all the formulas that you have, that from there you know that how the energy will be deposited. But what process will take place and where the particle will end up, all those things are randomly generated. Okay, that's a simulation. So a Monte Carlo simulation is a computer-based technique that uses a repeated random sampling to simulate a physical processes, such as a path and interaction of protons in a patient's tissues or in a phantom. Okay. So this is what the definition of a Monte Carlo simulation. This is, I just took it from Google. Okay. Rather than there are volumes written on a Monte Carlo, radiation transport and all kinds of things. And I thought that this summarizes very well. You can just type Monte Carlo simulation in a proton therapy and it will give you these things. Okay, you will read them. So for the sake of discussion, that's what, and in proton therapy, it models how a proton beam is delivered and how a proton interacts with the patient geometry or phantom, including generation of secondary particles. Okay, how much energy it is going to, suppose you say that, okay, I get a random number from which I can determine how much energy it is going to lose at that particular location by ionization. Then that secondary electron comes out. Then you follow the secondary electron. All those paths are being followed as the particle is moving through. But if you do that experiment of determining the area of a irregular region inside a square, if you do only 10 or 20 random sampling, your results will not be accurate, because that probability is very small hitting that region. So in order to get a very statistically significant, statistically accurate result, you have to have many histories. You have to do many sampling, millions of sampling. That's what they do. But you are not doing it, the computer is doing it. So that's why, because of the availability of high-speed computers, this Monte Carlo simulation process has become possible now. So why you need a Monte Carlo? Because measurements have its limitations. And also, you cannot do measurements in all conditions, because that is very difficult to produce. Because what happens inside a patient, how much dose is given, we calculate in the treatment planning system by a model. But you have to verify it by another means. The gold standard is measurement, but we cannot put a detector inside the patient. We can do good phantom measurement inside the phantom and all kinds of things, but our ultimate aim is what? To measure the dose inside the patient, or or determine the dose inside the patient. So Monte Carlo simulation helps you. It's another way of verifying it, independent way of verifying it. Of course, garbage in, garbage out. If your Monte Carlo is not properly simulating all the physical processes, or is not sampling enough, there will be uncertainties. So all the Monte Carlo simulation has to be validated by measurements. So this is the Monte Carlo model of your beam based on the measurement. Your measurement may have inaccuracy. So if you use inaccurate data for modeling your Monte Carlo will not give you good results also. So this is a catch-22 situation. How do you really create a good Monte Carlo model? So eventually, just like now in machine learning or artificial intelligence, you do measurement. You do your measurement where measurement you think can be very accurately done. Okay, large fields where detector size effect is very small, and then you use that data to validate your Monte Carlo. Okay, and then do some Monte Carlo measurement on a different data set that which you have not used to model your Monte Carlo, and again verify them by measurement. Of course, the measurement has to be valid. You have to have. That's where the skill of the physicist comes into play. Okay, that's why they employ physicists, not ask anybody else to go and do it. Okay, so you have to have a good measurement skills. You should know that okay, the measurement that I'm doing has taken into account all the uncertainties that can be contributing to it, and I have corrected for all of them. Okay, so this is how the Monte Carlo model is validated. You have a separate data set to make the model, generate some data that the Monte Carlo results that for which you can also verify. They should not be the same data that you have used for modeling the Monte Carlo, for configuring the Monte Carlo model. Okay. High accuracy, patient-specific planning. Now, once you know your Monte Carlo is validated, well validated, you can do your you can take the patient CT scan and do a calculation also. Another way of verifying the Monte Carlo is you can take a random phantom, a phantom where you can put a film in different locations, you can put TLDs, thermoluminescent dosimeters, and do a plan in the Monte Carlo, do the Monte Carlo dose calculation, and then irradiate the phantom and read those kinds of things. That is also what we do in the beginning during the commissioning process. We also do the dose calculation not of our patient for CT scans, but do a CT scan of a phantom where you can do an actual measurement inside that phantom, realistic phantom, tissue equivalent phantom, that which is simulating how the patient looks like. That's called a random phantom. Okay, this is available. That and they have bony areas, they have lungs, they have also different kind of phantoms are available, which mimics the body of the patient. And but the good thing is we can create holes in that phantom or create a space for a film to put in. Even you can put an ionization chamber also. That you can do accurate measurement to validate both your Monte Carlo or your treatment planning system and all kinds of things. So physicists are good at these kind of things. Okay. I'm not going to spend too much of time on Monte Carlo. So how it works, it is written here. Software, there are softwares available, giant four topaz, so trajectory and energy deposition of individual protons and other particles as they travel through the patient's body or media of interest. The simulation tallies the total absorbed dose at many points in the patient tissue, creating a detailed 3D dose map. So when you are talking about validating the IDD curve measured by the Bragg-Peak chamber of volume size, in that case, the scoring region, in Monte Carlo, you have always a scoring region where you score the dose. If you are trying to verify the measurement of the Bragg-Peak, then you create a region which is exactly matching your Bragg-Peak volume, and score it and compare it. Then you see that if they are matching, then your model is good. But you wanted to see if everything is being, the volume, the size of the chamber is good or not, then you increase that volume and see how it is converging. That way you validate your IDD measurement by a finite size detector. The detector has a finite size, it's not infinity, but you can create an infinite scoring region in Monte Carlo. It's your just choice. You can say that, okay, my scoring region is 20 by 20, has a diameter of 20 cm. Then you have already validated what the measurement, what the results looks like in a 12 cm region. Then you calculate it in a 20 cm region. You compare it. If the 12 cm region is matching with the 20 cm region from your calculation, then the IDD curve that you get to 12 cm is good. It's converged. The size effect is not there. If you see that 20 cm is giving substantial difference, then your spot profile tails are not being properly measured with the Bragg-Peak chamber, so you have to correct for it. That's the detector size correction, you have to apply it. You don't have to apply the correction, just take your Monte Carlo data and use it. Okay? But the Monte Carlo data has to be validated, at least in the 12 cm region, whatever you are getting measuring, and that is also giving by the Monte Carlo. Because the detector is not able to measure everything, so also Monte Carlo. Monte Carlo is not also able to measure everything because you are restricting your scoring region to the same size as your detector. Okay, that's how you validate Monte Carlo. But then you check your convergence of your results with the detector size by doing measurements at a different for different detector sizes. Okay, so the experimental data. Okay, fast and accurate Monte Carlo simulations are vital for techniques like adaptive radiotherapy, where treatment plans must be rapidly updated to account for changes in patient's anatomy, all kinds. Okay, so Monte Carlo has many uses, but we are discussing now the commissioning part. The Monte Carlo simulation plays a very significant role in validating your data that you are measuring. Okay, let's go back to where we are. Okay, so this is where we have the Bragg-Peak chamber. In the early stage, when we started our scanning beam in 2008, this is the detector that is only available. Then we found out that this detector is not good enough. The diameter is not large enough to measure the complete integral depth dose, specifically for low energy beams, which the tails are pretty large far away. And for high energy beams also there are some tails that are responsible for contributing to something called a halo dose, because that thing, if you don't take into account the tails properly, then your calculation for patient fields will be smaller than what you measure. So that's why this Then we published those results, and then the manufacturers started creating larger chambers for doing IDD measurement. What is the problem in creating a very large chamber? Because eventually when you are doing ion chamber dosimetry, there is a bias being applied, okay? Because you have the charge that is collected by inside the ion chamber, they has to be collected. So there has to be bias being applied. And as you increase the volume or size of your chamber, that bias may not be uniformly distributed, okay, when you apply to such a large area. So that's why the collection of the charges may not be efficient. So there are certain limitations in designing very large detectors, okay. But very large detectors, you have to spend a lot of money, lot of all kinds of things, design such kinds of things. In high energy physics, in experiments, they have very sophisticated detectors, okay, very large detectors. Those people who are working on detecting what is that, neutrino and all kinds of things, they have to make very huge detectors because the neutrons, the probability of hitting some volume is very low, okay. So that's why you have to have very large detectors. But we are doing in a laboratory that where you wanted to measure the dose, and if you have very large detectors, how you put and how you measure phantom, all kinds of things. So 12 cm shape nowadays, the spot sizes have also gone down because of the technology, development in technology. So a 12 cm detector looks to be sufficient, is found to be sufficient. But then we validate with the Monte Carlo data. So, okay. So these are some data we have taken with this Bragg peak chamber. And the lateral fluence is measured by film, OSLD and the scintillator plate. When you are measuring the small ionization chamber is also used to do the profile measurements. Small ionization chambers have some size, so if they may affect the profile, the accuracy of the profile measurement. So you have to do if you are using ionization chamber, you have to do a detector size correction. Film size very small, the size effect is very small because very the spatial resolution is very small, or very good with you can have a sub-millimeter level determination of dose in sub-millimeter level resolution. You can do that measurements with the film. OSLD detector size effect is not that much because the size is very small, sub-millimeter. For finish, the scintillator plates are just like the film also. So these are some measurements, but films have their film dosimetry is very tedious. You need to have enough patience to calibrate the film, and the optical density that you get after exposing the film to radiation, that is affected by many factors. So films has to be film dosimetry requires a lot of careful attention to those details. So basically you have to have a calibration curve by comparing with ion chamber measurement, and then use them. So every film has a calibration curve that you have to use. Once you have that calibration curve, then you can see that how good it is compared to your ionization chamber measurement, and then you use the film. Film gives you very fast dose distribution, so that's one advantage. It has a higher spatial resolution, and you don't, and it's less time consuming to get the film exposed. So this is what we did. We did a calibration curve for the film, and at a different location of the proton beam. Then we compared with the ion chamber and then started using it. So it looked good. But then what we found, this is the EBT film here. If the dose is pretty low, then the film dose in that region the film doesn't agree with ionization chamber and other methods. So that's why there's a limited region where film can be used. After that, your film data doesn't look that accurate. So you have to have this kind of investigation. Of course, we have ion chamber measurement, and we did the OSLD measurement. And OSLD is optical stimulated luminescence dosimeters. Okay, so we got some special ribbons which you can get a line profile and all kinds of things, but that is no longer available. So of course then we got this where is that one, I probably lost that the Phoenix, the scintillator plate is commercially available now, so that helps. Okay. So these are some data that is showing we have taken for different energy. There in here profiles that we measure how these spots look at the extension, the spot sizes as a function of energy. That's what we're looking at. But then you see there is in air, the spot size in the x and y direction are different. It is not a circular or it's not a circular shape, it's an elliptical shape. So that worried us for a while, but then in water, because of multiple Coulomb scattering and all kinds of things, that difference gets reduced very much. X and y, they become much more circular. In air, they have some difficulty. They don't have, they are not circular, but in water itself, because of multiple Coulomb scattering and all kinds of things, that difference gradually gets reduced. So we can assume that the spots are circular in the Gaussian in x and y. The difference is much smaller. But anyway, you have a Gaussian in x direction, you have a Gaussian in y direction. Then you can fit accordingly and use them. But most of the time, treatment planning systems they assume that that spot is a circular spot. But it is possible because in water the difference is very small. That assumption is still works well. You see the spots are looking like a Gaussian, and if you do some analytical calculation assuming your detector response is a Gaussian, then you can deconvolve and then find out the true profile. Okay, when you do the measurement, the measured profile is a convolution of the actual profile and the detector response. So you are measuring the convoluted profile, and if you assume your detector response to be Gaussian, you can deconvolve. There is a process called deconvolution. By deconvolution, you can determine the actual profile. Okay, so we try to do that to see the profiles that we have measured in the ionization chamber. What is the effect of a detector size? So what we found is the detector size effect on the profiles is rather small. Okay, it's not that big. This may be a consequence of a small second gradient of the lateral profile function in most of the region beyond the peak of the Gaussian-like function. The detector size effect is important in the non-linear region of the profile. Non-linear region of the profile. Suppose you have a linear region. In a linear region, you put a detector. Some region will get a high dose, some region will get low dose. But it's a linear, so if you average it, then it will become the dose that are the center of the chamber. So linear region, the detector size effect is not there. Okay, it's very simple. Do you understand what I'm trying to tell you? In the linear region, let me use the chalk here rather than moving. Yeah, it's there. You have a Gaussian profile. Okay, your Gaussian profile. Suppose your detector you are measuring here. Okay, this is the center of the detector. In this region, the dose is higher than the center, higher than the center of the detector, and in this region, the dose is lower than the center of the detector. But this is the same amount. It's in the same amount. So if you add this is x0 in this region, another point plus delta x plus x0 minus delta x divided by 2. You take the average of this. One point increasing delta x, another point in the beyond one point is decreasing by delta x. So and you take the average of this cancels out, then 2x0 divided by 2 is equal to x0. Okay, so that's why what happens is if you are in the linear region, the detector size effect is not there. Okay, but what happens in this region, there is a second gradient here. Here there is a second gradient and it's no longer this linear. So those are the regions where the detector size plays an effect, okay, has some effect. Okay, would you remember this? You will remember this, that the detector size effect is important only in the non-linear region of your profile. In the linear region, it's not important. Okay, and most of the Gaussian, most of the profile is in the linear region. So that's why it's not that important. But if it's not that important, you don't neglect it. So that's why you use smaller detectors, diodes, very small region, or scintillator plates that I showed, the Phoenix. So that's the better way of doing it. But all those detectors, they have to be, their measurement has to be validated by comparing with ion chamber measurement. But if you are doing ion chamber measurement with a detector with some size, that profile will not match with them. So how will you compare them? You correct it for the detector size, then compare it. If it is matching, then you are happy. Okay, you can use the small the better with the detector with a better resolution and no detector size effect for all other measurements. But you have to validate it first because ion chamber is the gold standard. You make sure that the other devices which has some effect like response to LET dependence, dose dependent response, and all kinds of things, making sure that okay, those things are not important in the region where you are measuring, comparing with ion chamber measurement. Okay, so what you do remember, ion chamber measurement is the gold standard. Okay, that is the most accurate method. Sometimes they are tedious, sometimes they have a detector size effect, but we need to do a fast and accurate measurement. For doing a fast and accurate measurements, film and scintillator plates and diodes, those are very useful. Diode arrays, they are helpful, but they may have certain other effects that gives you, may not give you a correct profile. So how do you validate that? You compare with ion chamber measurement. Ion chamber measurement has the detector size effect. If you believe there is a significant detector size effect, you correct them by applying a correction method by deconvolution and then compare them. If they are comparing well, then you have green signal to use the other detectors. If not comparing well, try to correct the readings of the other detectors to take into account what might be affecting their response. Okay, does that give a good summary of what the detector size effect and what to use to do these measurements? Why I am telling you this? Because the profiles of the spots of the pencil beam spots are very small. Measuring them, the profiles, is a challenge. Okay, so how do you overcome that challenge? Use small detectors. Use high resolution, especially high resolution measurement. Okay, so but those measurements may have certain artifacts because of their response may be dependent on many other factors. So how to correct them? Okay, that's what I am telling you. Okay, so okay, let's move on. Finish up. So do you know what IDD is? IDD is integral depth dose. Okay, integral depth dose. That means you are integrating the contribution of the spot on a plane. Okay, and that is what is used for calculation, because the formalism is that you take IDD and then multiply with the contribution of the profile contributions, which are modeled by what? Modeled by Gaussian. Okay, this is what the detector size effect. How to check the detector size effect of your Bragg peak chamber when you are doing IDD measurement? Okay. if you don't use a large enough chamber to measure the contribution of the whole spot, what you will miss? You will miss the tail contributions. Those tail contributions has a name that's called a halo effect. That means, so that halo effect can be as much as 14 to 20%. How the halo effect was known? Because they suspected there is something that missing. When they try to do measurement of dose at the center of a concentric circles, fields of concentric circles with different radius. So you do a measurement at the center of a 5 cm circular field, 10 cm circular field, 20 cm circular field, and they did the calculation with their analytical model, and they found a different. They found some difference, and then they added some other correction to the beam model, and to take into account the contribution of the long tails that may be missing, and then after they added that correction, everything matched well. So they gave it that, okay, what we are missing is a long tail contribution of these profiles, and they call it a halo effect. Who are they? You didn't ask me who are they. We also discovered that by doing the integration method, but it was also when we are doing this, when we found that, okay, something is missing in our measurement and in our calculation, we looked at the literature. Before we started our scanning beam treatment, there is another place in Europe that's called PSI, Paul Scher Institute. They have been using spot scanning beam before us. We knew that, but we didn't look at what they have done. So they had published a paper and showing this effect, that if you don't use a large enough chamber to do your IDD, you will miss the tail contribution, and that tail contribution will make your neglecting that tail contribution, you will not get a good the results for your dose for different field sizes. Okay, and that's how they call it a halo effect, and everybody is calling it a halo effect, but I call it the long tail effect of the spot profiles. Okay. All right. So how do you now? You have all the measurements. You have done the IDD measurement. You have the profiles. And also it needs a absolute dose calibration also. Absolute dose calibration means you create a volumetric field. You create a volumetric field and put an ion chamber and find out what is the dose you are giving, and that is our absolute dose measurement. Absolute dose measurement, you take a chamber, put in a volumetric field, broad field in a large volume, and then irradiate that field to the chamber. The chamber is put in the field, and then you measure the dose, and that gives you the absolute dose. And the same thing in the treatment planning system also have that exactly the beam that you have used to do that measurement is also in the treatment planning system, and you give that dose. Okay, if you use that field, this is the dose you will get at that point. Then treatment planning system uses that to calculate absolute dose for other fields. So for commissioning the spot PBS in a treatment planning system, you need IDD, you need spot profiles, you need absolute dose calibration. These are only three things are needed. And what are the steps for commissioning it in treatment planning system? Enter and configure the machine description, that's in a beam administration. Provide required beam data that I discussed. Verify TPS dose model is correct. Compare phantom measurements with calculated dose. Once you model the beam, then you calculate for various situations, various field sizes, and then measure them, and make sure that they are agreeing with what the treatment planning system is calculating. Then if you agree, then your model is correct. You can use it for patient treatment planning. If not, what do? You go back and change the parameters that the beam model is using. That's how it goes on. It's an iterative process. He is our expert on beam modeling in treatment planning system. We have luxury, have design one person who takes care of our treatment planning system. Okay. Sometimes different models are needed for small and large treatment fields and with energy observers. What happens is the treatment planning system is modeling your beam with certain parameters, and those parameters are fitted to your measurement data, and that model may not be giving you predicting the dose for all situations. It may give you good agreement for large field sizes, but may fail for small field sizes. It may give, so that's why sometimes if the difference is very large, you create different models. Create a beam model that is good for small fields. So anytime a patient has needed a small field, you use that model to do the dose calculation. Anytime you need a large field, you do the other model. The beam model that is good without energy observer may not be good for with energy observer, because the beam data changes when you put the energy observer in the path of the beam. Okay, so that's why sometimes you have two models, that energy observer model and without energy observer model. Not all patients are requiring energy observer in their field, because only you use energy observer for the targets which are close to the entrance of the beam. So that's why if that situation happens and your treatment planning system is not giving accurate dose both for fields with energy observer and without observer, you create two different models, but you choose your model accordingly that what you are using for patient treatment. But this is prone to error. Sometimes the treatment planning, the people who are planning, they may forget it, and then it creates more work. So it is desirable to have one model which is valid for which works well for all of them. So that's why in the initial phase, the treatment planning systems were using analytic formula to do their dose modeling, the beam modeling. Then there was some interest in using Monte Carlo as a beam dose calculation engine. So that way these limitations can be avoided. Okay. Okay, we have done with this one. So these are the data. As I told you that in our beam, we had 94 energies. All the 94 energies were not measured. They were taken from Monte Carlo data, and this is our Monte Carlo guru. Okay, so he gave us a Monte Carlo data for this, and this is being used in our treatment planning system. Okay. We have that, I tell you again, we have that luxury. We have many people. The department have 100 physicists. So naturally then that we can do all kinds of things. In a small place it's difficult. Okay. But most of the times the proton centers are not located in small places, in big places. Now it is changing. Everybody wants a proton machine. And so that's why they may have some difficulty in doing very rigorous commissioning process, going through a rigorous commissioning process and all kinds of things. The good thing is, as many people start using, then you get a standard data so that we can use it. You don't have to really do in-house verification and all kinds of things. Okay, you can rely on other people's experience. Okay, so this is what happens. This is how the dose is calculated. You have two Gaussians. You have two Gaussians and depth dose curve, and you sum it, and that is how the spot profiles are calculated. And then you have the width, the spot sigma. You have these models A1, B1, C1, and there is a weight here. These are the models. This is depth dose normalization factor here. Depth dose normalization factor here. This is the profile. This is the profile. Depth dose norm. This is the dose depth dose normalization factor here, and these are the parameters. These are the parameters that are being adjusted in the treatment planning system from your measured data. So you fit something and then use it to calculate the dose, and then okay. So he created he created 430 kind of targets, different kind of the beam fields to test the model, and all those measurements were done, And how do we do the measurement? We put an ion chamber in a water tank and deliver those 430 treatment fields that he generated from the treatment planning system, and then we measured it with ion chamber. Then what happened? Then we started comparing. So these are the comparisons of a different calculated and measured and calculated value are being compared to validate the model in the treatment planning system. And these are some differences that we found. You can see some of them are well beyond 3%, and those are the problematic fields. So the model needs to be further adjusted. Okay, this is about better. There is still some of them are very large fields. There are some disagreement. So for which that the average value data before renumeration was about average value is 1.7%. But average value is not always a true representation of how your model is valid. Okay, you would like to keep everything within 2%. Okay. Okay, so these are some volumetric dose calculations for constant field sizes, all kinds of things, and this is how SOBP calculation was compared with the measured data. And this is some irregular field. Look, the agreement looks good. So this is a irregular treatment field. This is a comparison profile that look good. Okay, now this is I showed you for a eclipse. Okay, then the question is that how to do for other treatment planning system. The ray station is another popular treatment planning system. In the afternoon, I have invited a planner from a person from ray station to present you how the ray station is used for proton treatment planning. Okay, he will give a 1 hour presentation to see how the treatment planning is done in the ray station, because I cannot log into my ray station and show you. And whatever I show you also has the patient names and all kinds of things. So I thought that is the best way to do. Ask him if he agreed. So he will give a talk to you, and you will hear from the expert. Same thing, not much different. There is a backpeak data, integral depth dose, lateral profile in air, and absolute dose in water. Then configure the beamline and validate the model. So there's not much difference. Only thing is, for eclipse, you need large amount of data. For ray station, they are using a Monte Carlo to configure the Monte Carlo data. They need limited number of data. So that's a good thing. So that configuring a ray station, a PBS in a ray station is much easier compared to eclipse. And a good thing is, you give them your data. A ray station asks you to give the measured data, and they will give you the beam model. You don't have to spend time to fit the data and all kinds of things. That's a good thing. Not many people do, but a ray station do that one. So that's a good thing. Okay, so we are done. How to do the treatment planning configuration? You know already how the beam is generated. You know what the machine components are. You know how to do absolute dose calculation. You know how to configure a treatment planning system. Now you are ready for what? To do actual treatment planning. Okay. Actually, I have to tell you something I forgot. Do you understand why you need a stopping power ratio between water and air when you are doing ion chamber dosimetry? I mentioned that many times because that requires, in absolute dose calibration and all kinds of things, you need the knowledge of a stopping power ratio of between water and air. Do you understand why? You never asked me at that time, because I know that most of you have not worked in the clinic, so probably you have not gone through the basic course of radiation dosimetry. I just assumed that you know it, but then suddenly I thought that you may not be knowing it, why you need it. When you irradiate the ion chamber, what is the material that you are using, irradiating? What is the charge you are measuring? The charge is generated from where? The air, inside the air. You are not interested in the dose to air. You are interested in dose to water. So that's why whatever dose you get through the air, you have to convert it to the water. So that conversion requires you to know how the stopping power of water compares with air. So that's why you need the ratio of stopping power of ratio of the water and air. So that's why S W air comes up in all those equations. Okay, for ion chamber dosimetry only. For ion chamber dosimetry is based on ionization of the air. You are interested in dose to water. So that's why you have to know what is the ratio of the stopping power for water and air. Okay, and that depends on the energy also. Okay, for energy, it is energy dependent. So if you are doing measurement at a different location where energy is changing, then you have to have that correction for energy. Okay, and in protons, that ratio doesn't change very much. So that's why you can straight use the ionization curve as a PDD curve. All right. What next? Okay. I think I'll skip them, but this gives you some idea what are the factors that affect the dose from relative to the reference condition. When you do your calibration, 1 centigrade per mu or whatever, in a reference condition, we have 10 by 10 field size. We put the chamber at the center of the SOBP. We had a 10 cm SOBP. We have 10 cm field size. The medium is water, and we are doing a measurement on the axis, central axis. But in calculating, our interest in dose may not be exactly in that condition. We may have a field size that is using for patient different. We may have a SOBP that is different in the patient. We may have a different location. The point is not always in the central axis. It is not at the isocenter. So how do you calculate those things? Those things affect the dose and the point of your interest. Okay. So these things can be given some specifically for passive scattering beam. They can have some. They can given a name of it. We can characterize them by different factors. Our calibration was done in a particular beam energy. If you are using a field of different energy, then if you know how the output changes with the energy, then you can call it a relative output factor compared to a reference energy. Okay. So if you are using a different SOBP compared to the reference SOBP, we can call it a SOBP factor. Okay, and you measure them for a different SOBPs. You measure how the dose changing compared to the reference 10 cm SOBP. You call it a SOBP factor. And then you use a range shifter that's a different. In the reference dosimetry, there is no range shifter. There is nothing placed. Now you are putting a range shifter. So you can call it that as I add range shifter, how the output is changing, a range shifter factor. Okay, so. Same thing here. If your calibration point is not at the center of SOBP, you can call it an off-center factor. If it is off-axis location, you can call it an off-axis factor. All those factors I am telling you that you can characterize them, but how will you get their values? You have to do the measurement, okay, or do calculation. Somehow you have to get their values, and then source to calibration point distance may not be the same as that used in a reference condition. You give a inverse square factor. If the field size is different, you call it a field size factor. If you are using a compensator and there is a different, because the reference condition, the calibration was done in water, and in the patient it's not water. There are many materials in the patient. They have a different scattering properties. So you can consider that as a patient scatter factor. Okay, and now in the reference condition, you are not using a compensator. Now you are using compensator. You can call it a compensator scatter factor. All those things contribute to whatever the final dose for that field at the point of your interest. Okay, so this is something, a formula that what I am saying is the dose in a non-reference condition will be vastly different than your reference condition, and how you are going to quantify them, how you are going to calculate them by hand. Okay, so eventually these things are necessary to do a monitor unit calculation for a treatment field, how long the machine has to be on. Okay, so that is necessary for the passive scattering beam when you are using passive scattering beam for treating patients. because the treatment planning systems do not give that monitor units, calculate those monitor units. You have to calculate yourself or do a measurement. Most of the places which use passive scattering beam, they do a measurement approach, just to take a water phantom and irradiate the field and determine the dose that how much dose you are getting for certain MU, and then determine how much MU you are going to give for actual treatment. We wanted to do a hand calculation, by hand calculation, how we can get that MU. Those of you who have worked in clinic, nowadays, because you are doing IMRT, the IMRT MUs are calculated by treatment planning system because inverse planning. You cannot calculate by hand for those complex fields. So you do a measurement to verify that your dose that you are calculating, predicting by the treatment planning system is accurate. So passive scattering beam, we can do that hand calculation of how long the beam has to be on. But it is also always verified by measurement. Since not many places are using passive scattering beam, I am just giving you this thing for the sake of some information, okay? So if you want to do a measurement of your MU, if you want to do a measurement of your MU for a treatment field, you are not measuring in the patient, you are measuring in a water phantom. So eventually what you do is, in your treatment planning system, you create a water phantom. And whatever the field that you are using for the patient, use that field to irradiate that phantom and calculate a dose at that particular point. And then you do the exact same setup in your treatment machine and irradiate that field and see how much dose you get. From there you can verify the dose or calculate the monitor units. That's the best way, simpler way. But in a complex way is this one, by you take all these factors and then calculate your MU. I'm going to spare you from that trouble of knowing it, okay? But this is also can be done very easily. The MU can be calculated by dose from the plan, dose per MU per plan, and you do it in the water phantom. From there you have all these factors, and then eventually that MU will be dosed to a water without any compensator, and dose per MU per water no compensator, and that's this MU and this MU are same, okay? So this is how we did our passive scattering beam. No worries, I could have completely skipped this because I don't want you to spend too much of time thinking about the passive scattering beam, which is no longer being used at many places, okay? So let's forget it. Okay, this is the important thing because we are in the modern age, okay? Age of smartphones. You have everything on your in a how many 6 cm 10 cm device, okay? So spot scanning beam is now the preferred way of treating the patient. And almost all clinics, only one center, that Loma Linda, which is the first hospital-based proton center, they have not upgraded their system to scanning beam, okay? They still use passive beam. That's the only center I can think of. We have stopped using our passive beam. It's done. We are no longer doing it. So that's why I not feel good that I didn't give a in detail description of how to do a MU calculation of passive scattering beam. If you want, on the Sunday, I can give you some example. You can do some exercise if you have time, okay? But it's not important. So for proton pencil beam scanning proton beam, the dose at any location is sum of a spot dose at the point of interest, okay? As I showed you before, okay. So you take the IDD and multiply with 2 Gaussians, then you can calculate the dose at any point. We have already discussed it. The broad field dose is calculated in the treatment planning system is verified by measurement. So nobody does a hand calculation of the monitor units that you need to deliver that field. It's calculated by the treatment planning system because it's inverse planning. So what in the inverse planning it does, it first assigns one monitor unit to all the spots, and then the spot weight is optimized to give you the dose distribution. So once the spot weight is optimized, then it sees that what is the weight of that spot. It started with 1, but now it has become different, less than 1. So from there it calculates that, okay, what is the absolute dose that is this spot is contributing to your point of interest, because the commissioning is done not in a relative dose sense. It is commissioning is done in a absolute dose sense. All the profiles are given the absolute dose. All the IDD has the absolute dose. It's given in. It's not a normalized thing. It is not relative dose. Whereas in passive scattering beam, everything was done in a relative sense. Okay. In this case, all the dose information is given for that spot profile, the IDD. They already are calculated according to absolute scale. Every spot, it gives you that how much exact dose it is giving at what location. So once you have that information, then you have that how much at each point the dose per mu. So once it calculates the weight of the particular spot, then it can calculate how much mu it is needed. Okay, so the treatment planning system will give you the monitor units, all the information, because of this nature of commissioning. And then of course it may make a mistake. So how do you do? How do you verify them? So to verify them, you do a measurement. As I mentioned, you create a water phantom, irradiate that spot pattern to the water phantom, and determine the dose at a particular location, put an ion chamber, you measure it. Or you can put a film or a array detector to do that dose measurement and compare the planar dose with the calculated planar dose. Of course, you are measuring in water and you have to do the calculation in water. That's called every treatment planning system gives you an opportunity to do this. They will ask you after the plan is done, then you do a QA plan. You do a quality assurance. QA stands for quality assurance. You do a quality assurance plan that in that case it will irradiate that treatment field to a water phantom, and you will give a dose distribution in that water phantom. Then you decide which depths you are going to do measurement. You take your detector, put at that depth and do a measurement and compare with the calculated dose with your measured dose, and that's how you verify. Okay. Of course, you can always do a hand calculation. If you have the IDD information at that location, you can take a Gaussian and calculate that value of that Gaussian function at that depth. If you know the sigma x, you know the coordinate of, and then you can verify. It's a good exercise. It's a good exercise. If you want to do, you can do it. Okay, but nobody does that one. Okay, because it's easier to go and measure with a chamber, and that is needed also. That's a part of our quality assurance process. Every patient treatment field has to be measured, making sure that you have no problem with the delivery. Okay. So this is my last slide probably on this lecture. This is we just talked about the dosimetric part of the commissioning, the verification. But treatment planning, treatment of the patient requires many other things. Okay, you have an imaging system. You have also you have a record and verify system, and all of things that you have to also make sure they are working properly. So then what happens? These are some of the other commissioning tasks you have to perform. The IGRT, image guided radiation therapy. If you have a cone beam, making sure that a cone beam isocenter is matching with the treatment isocenter, and the cone beam quality is whatever is required. What is the specification by the vendor or whatever acceptable according to different regulatory bodies, that you have to verify. Make sure that the cone excision is okay. X-ray field edge coincides with the proton field edge. So of course this is not that important because we are no longer using aperture. But if you are using aperture, how do you know that the aperture is correctly manufactured? So you have to take an X-ray of the aperture and compare with the planned aperture. But if your X-ray system is not working to give you the correct picture of that aperture, then there is no point in comparing. So you have to make sure in a standard aperture that the X-ray system edge, field edge is matching with whatever field edge you are expected to have. Image alignment system, that is a software that makes sure that image alignment system is working okay. You have a record and a verify system in which the patient treatment information is sent, and the record and a verify system is sending to the treatment control of your delivery machine. They communicate properly, and also that it is flawlessly working. Eventually, before you release the patient to the room for a treatment, you have to do an end-to-end test with a phantom. Take a phantom, do the CT image, then do a plan for a particular region of the target, send that plan to the record and verify system, do a IGRT, verification of positioning that phantom in the beam, do a beam delivery, then do a dose verification. Make sure that dose you delivered is matching with the treatment planning system. Then of course you have to take baseline data for your machine QA, because you are going to do periodic machine QA. Make sure that you take enough data to check the constancy of your daily QA, quality assurance, daily, monthly and annual QA checks. That will make then finally your room ready for patient treatment. Okay, so these are the things you have to do in order to get your treatment delivery system to be used for patient treatment. So now you are ready to do patient treatment. Okay, let's go do some treatment. Yeah.